Any questions before we start rock and rolling? So the last time that we were all together, yes, this is the set of this is a set of all automorphisms from F to F that fix K. So in other words, not only these automorphisms, but they're K, they're K vector space linear transformations as well. Sometimes I call this aught FK or G of FK. This is called the Galois group of FK. So for example, here, D is a square free integer. And let me briefly remind you that what I mean for it to be square free is it's not divisible by any square other than one. Anybody know what the automorphism group here is? Q radical D over Q. Okay, let me point out that of course there's always the identity automorphism, right? So let's forget about that. The identity automorphism that takes everything in Q radical D to itself. Okay, that's an automorphism that fixes Q, right? Is there another one? Well, there's also does anybody like remember back to like high school and stuff where your teacher might say, rationalize this, right? Right. It's probably a bad idea if you're teaching a pre-calc class to say, hey, stupid, just use an automorphism. Bad idea. Don't do that. But that's what you're doing, right? When you rationalize the denominator, you multiply by the image of this under a certain automorphism. The way it works is this is conjugation. This is often called conjugate automorphism. Notice this one is a non-trivial automorphism, and notice it also fixes Q, right? Because what does it mean to be in Q? It means to be a zero, and this automorphism behaves like the identity as well on Q. Everybody okay with that? So that's it. So the Galois group of this is actually isomorphic to Z2. Right? And again, Z2, you can see the structure here because what happens when you compose sigma with itself? You take A plus B radical D, you conjugate it, and then you conjugate it again, and you get the identity. So notice that when this squared is the identity, so you get this Z2 structure. Okay, math's all about analogies. So how about that? Anybody out there want to guess what the automorphism group of the Q group 2 over Q is? This is actually a trick here. this one is the identity. The only automorphism you get that fixes Q is the identity. And actually, I'm going to expand on this to show this a little. In fact, I'm going to look more extensively at this field here. But suppose you have an automorphism. Let's say sigma Q root 2 Q. I'm going to expand on this later, but I'm going to make a very critical observation. What are the options for image of group 2? What options do you have before you? This is one of the most important questions to ask in the development of Galois theory, right? So here's what I'm thinking here. What I know so far from field theory is this thing has a basis over Q, right? This is an extension of degree 3, right? Because the minimal polynomial of cube root of 2 is x cubed minus 2. Everybody agree? So this is a field extension of degree 3 that'll have basis 1, cube root of 2, and the cube root of 4. If I want an automorphism that fixes Q, as all good automorphisms should, I know what to do with all the coefficients, the Q's. So really, my big question is, what are my options for where I can send cube root of 2? Well, notice that let's send it somewhere. Let's call it alpha. Right? Well, what can I use to help me out here? Notice that sigma of cube root of 2 cubed should be alpha cubed. Right? I mean, really, I'll just cube both sides of this. And this, because of the fact that this is an automorphism, should be sigma of 2. And sigma of 2 is 2 of this rational, is a rational number. So from my little computation here, I can draw a conclusion, and that is alpha, the image of cube root 2 must be a root of, because alpha cubed minus 2 is equal to 0. This is actually a very important observation. The image of the cube root of 2, which is a root of x cubed minus 2, has to go to a root of x cubed minus 2. That's it, right? What are the roots of x cubed minus 2? They are cube root of 2, omega cube root of 2, and omega bar cube root of 2, where omega is the primitive cube root of 2. It's that complex number. Everybody cool with that? So no matter what, my sigma has to take cube root of 2 to one of these 3 animals. But notice that sigma is, by hypothesis, an automorphism of this, which means it has to stay inside here. Now, if the cube root of 2 goes here, That's impossible because the original field was a subfield of the real numbers, and this is not. By the same token, the cube root of 2 can't go here, which means under this hypothesis, the only place that I can take the cube root of 2 is to the cube root of 2 itself. So now what have I done? I have fixed all the rationals, I fixed the cube root of 2, so I fixed all the powers of it, so I fixed every element in this thing. And so the Galois group, that is the group of automorphisms in this field that fix the rationals, is merely the identity. Any questions on that? Any questions? Okay, I am going to make a table for fun. And because I think that actually you all are going to help me make the table. And this table, I think, is sort of a good prototype example that will help us understand the general theory of Galois theory we get at. So this table shows big chunks of this in action. So here, I am going to put this previous example on steroids. The problem is my field here from this example is too small. It contains one of the roots of x cubed minus 2, but not all of them. So I'm going to make a bigger field that contains all this. But alpha equals the cube root of 2, so I don't have to write that. And omega minus 1 plus square root of minus 3 over 2, the primitive third root of unity. Notice, let me point out that omega cubed is equal to 1, and omega squared plus omega plus 1 is 0. It's easy to check that. Now, what I want to do is I want to look at the smallest extension of rational numbers that contains both of these things. By the way, there's method to my madness, because notice that alpha, alpha omega, and alpha omega bar are the three roots of this irreducible polynomial over the rational numbers. That's it. That's the list of the three right there. And so basically I'm going to create the smallest field that contains all roots of this polynomial. So look at the smallest field that contains Q, and it contains the cube root of 2, and it contains that primitive third root of unity. Right. A basis by the way, we've got a homework problem this week that shows that the degree of this extension is 6, because the degree of when you join alpha is 3, and the degree of this is 2 because it's a quadratic. 2 and 3 are relatively prime, so the degree of this extension is 6. And I'll write down a basis. It's easy to verify that this actually is a linearly independent set. There's many bases. All the bases, of course, have 6 elements. The one I want to choose is 1 alpha, alpha squared, omega, omega alpha, omega this is the basis of Q alpha omega over Q. Now, what I want to do, so here's what I'm going to do. Y'all can help me with this. I am going to find all the automorphisms in this field that fix Q, basically by seeing what happens to the basis elements. here's my basis. 1 alpha squared omega alpha squared. And it's going to turn out, I can find 6 automorphisms here. And basically, notice at the end of the previous example, what did we notice? We noticed that any root of the cube root of 2, or the cube root of x minus 2, must go to another root. So basically, I'm going to induce these permutations by seeing their effect on the root. The first thing I'm going to do, silly, I'm going to put C and ID. This is basically permutation that takes one that fixes everything. Actually, you know what? Struggle with my colors here. Now, what I'm going to do is I am going to let me write down the roots here, and from here on out, what I'm going to do is induce the let me also notice that omega bar and omega squared are the same thing. Complex conjugate square are the same thing in this example here. So notice that any automorphism must take a root of x cubed minus 2 to another root of x cubed minus 2. Right? So basically, it induces a permutation of these 3 things, right? Because an automorphism, it can exchange these roots somehow, and then induces a homomorphism. Let's see what happens. Obviously, if I fix all these roots, then I have to fix everything, right? Because if alpha goes to alpha, omega alpha goes to omega alpha, and omega bar alpha goes to omega bar alpha, then everything has to be fixed for that to happen. Agreed? Now, let me do another one. I'm just numbering because this might help.
Giving them the name.
Right.
Oh, okay.
What I'm going to do now is I am going to find an automorphism that commutes these 2 roots and fixes this.
Oh, so you're just enumerating.
That's exactly right. I'm just enumerating. So V12, what that should do is I want to leave omega bar alpha alone, and I want to swap out alpha and omega alpha. So, well, of course, every one of these should take 1 to 1, but alpha goes to omega alpha. Agree? Because I'm going to try to do that, just swap these out. If alpha goes to omega alpha, what does alpha squared go to? Well, it should go to omega squared, alpha squared, and omega squared is omega bar. Everybody okay with that? Now, how do I figure out where omega goes? Oh, by the way, I flipped these out. So omega alpha goes here. Where does omega go? Well, let's see here. omega alpha goes to alpha, right? And alpha goes to omega alpha. So this divided by this is omega. So omega should go to, right? So this divided by this is omega. So this divided by this is where it should, so notice omega alpha divided by alpha is omega, agreed? So this over this is where omega should go. So it should go to 1 over omega, which is omega bar. Everybody okay? And finally, I can piece this last together because omega goes here, alpha squared goes here. So this should go to the product of these two. So it should be omega bar squared, which is omega alpha squared. Everybody okay? Let's try another one. Let's try 1 3. So in this case, what happens is I'm going to try to flip alpha and omega bar alpha. So 1 should go there, alpha should go to omega bar alpha. And omega bar alpha, which is not in the table, should go, right, omega bar alpha is not in the table, but that should go back to alpha. But we should be able to figure this out. Where does alpha squared go? It should go, yeah, it should go to omega alpha squared. Good.
So then omega alpha squared goes to 4.
What's that now?
Never mind, I think that was the.
Well, so omega bar alpha, you okay with? Okay, so everybody okay with this much? We also have that, in this case, what happens is alpha goes to omega alpha and omega bar alpha. Oh, I'm sorry, alpha goes to omega bar alpha. So we can use this, right? So where does, so for example, alpha squared goes to, so we want to know where omega goes, right? I don't have any information on that yet, but I mean, how can we get that?
So could we just square the omega bar alpha to get omega bar squared alpha squared?
Okay.
Or I don't
So,
know if
no,
is that like a proper like way to?
Sure. So her idea is you want to square this and you should go to the square of that. That is correct. So omega alpha squared, let's go to alpha squared. I think you unlocked it for us. Everybody okay with it? So in other words, so we've got this alpha squared. And now what we can do is figure out where omega goes, because omega alpha squared goes to alpha squared, and alpha squared goes to omega alpha squared. So let's see, if I take this divided by this, I get omega, and that should be this divided by this. This should go to omega bar. And now omega alpha, I can just put these two together. So 2 omega bars is omega, so this should be omega alpha. Let me make sure I got that right on the table. And let's just get it. Okay, how about this? How about this? In this one, what you want is you want omega alpha to go to omega bar alpha, and omega bar alpha going to omega alpha. So you want to swap those two out, 2, 3, and leave alpha alone. So I've got 1 in alpha to start me off here. And so alpha squared, like that. Agree? So in this one, alpha is left alone, and you swap out these two. Where does omega go? Well, let's use this. We know omega alpha goes here, and we know that alpha goes to alpha. So if I take omega alpha over alpha, I get omega, and that should go to omega bar over alpha. So this should go to omega bar. What's it?
We said to make a booster.
Correct. Right, this is the 2, 3 one, so it's swapping out those two groups.
So the nominee is, yeah, that's the next one. That's the next one, right?
Oh, I'm
Just,
sorry,
omega
so-
bar alpha.
We
Okay,
already
so,
have that, right?
so omega, oh, yeah, we can check it, I guess, right? You're right, it should go to omega bar alpha, and it's a good gut check, and that's exactly what we get. Good. So you're on the case. And omega alpha squared should go to omega bar. Okay, so I've got, I'm running through the permutations of the roots, which we've seen is basically all we can do. And we're sort of exhausting this. 1, 2, 3. So in this one, I go alpha goes to omega alpha goes to omega bar alpha, and omega bar alpha goes to alpha. Okay, so let's see what this one does for us. 1 goes to 1, of course. Alpha goes to omega alpha. And the square of this should be omega bar alpha squared. Okey-dokey so far. Now, where does omega go? Well, let's see. This divided by this is omega, so omega alpha divided by this omega bar is, right, so omega should go to omega bar over omega, which is omega squared over omega, so it should go to omega. And omega alpha should go to omega bar alpha. Right, because that times that, there you go. And finally, this should go to omega alpha squared, so this should go to alpha squared. Good. And finally, in this iteration, you have alpha going to alpha bar omega, alpha omega going to alpha, and alpha bar omega going to alpha omega. I think that's right. 1 goes to 3, 3 goes to. Oh, I'm correct. 1 goes to 3. Oh, we did. 3 goes to 2, right, and 2 goes to 1. Good. So this should be 1, and alpha. This is alpha bar, and the square of this is there. Okay, where does omega go? Well, this divided by this is omega. It should go to this divided by this. So it should be 1 over omega bar, which is omega. Where does omega alpha go?
Alpha.
Agreed. And omega alpha squared, it's like omega bar alpha squared. So actually, in this example, every one of the permutations of the roots gives me an automorphism of this field. Because notice that in my columns, all my outputs are, of course, elements of Q adjoined with alpha and omega. They're all in there. I'm gonna go a step further in this example too. And I encourage you to play around with this example because I think it illustrates stuff. One of the automorphisms up there is an old friend. Well, two of them are old friends. One of them is a very boring old friend, the identity. One of them is a more interesting friend. Does anybody recognize the automorphism phi sub 2, 3? The answer is not too complex. Yes, 2, 3 is actually the automorphism complex conjugation. Notice that it leaves the real stuff alone and takes these other basis elements and kicks in their complex conjugate. So the automorphism that swaps only the roots 2 and 3 and leaves the real root alone basically induces complex conjugation, right? So that's an old friend. The other ones are more exotic. Let me kind of draw you a picture here too. I'm going to draw you a picture that we'll talk more about this later. Hopefully it'll help to kind of flesh things out. Let me ask you a question. I got 6 automorphisms of this. Everybody agree? And they were basically permutations of the roots, right? All possible permutations. Does anybody remember how many subgroups of S3 there are? I think there's about 6 of them, right? Let me kind of look at examples. We have some subgroups of this. Let me draw the subgroup lattice, actually. So, okay, so you've got the big one, S3. Then you have the subgroup generated by, or well, let me just say the subgroup E 1, 2, 3, 1, 3. And this index here is 2. Everybody agree with me? And you've got the identity here. And now you've got these 3 little silly little groups of order 2. All order 2, so the index here is 2, and the index here is 3. Everybody okay? So if I were to draw S3, that would be a truly glorious picture of its subgroup structure. Right? There is a correspondence between what goes on here and what goes on in this table. And in fact, that is the crux of, so this is my kind of spoiler here. This is the crux of Galois theory, is there's a correspondence between this group here and the intermediate fields of the extensions that go between Q and this. notice that what is the field, what is the subfield of this that is fixed by the identity? Right? That is, what is everything in this field the identity leaves alone? It's everything. Agree? Right? So the identity automorphism leaves everything in the field alone. Right? Now, let me ask you this. What's the subfield of this that is fixed by every one of these automorphisms? That is correct. Because notice, of course, the identity automorphism leaves everything alone, leaves all the basis elements alone. But this one screws up alpha, for sure. This one also screws up alpha. This one doesn't, and it leaves alpha squared alone, but this one screws up omega, right? And well, now you're really kind of done because it screwed up all of these. So the only subfield that's fixed by all 6 of these automorphisms is just rational numbers. Everybody okay? Let me ask you this. What does it look like? I'm not going to go through a careful proof because we're building this kind of thing. But what if you look at these automorphisms, the identity and these last 2 columns, what does it look like the subfield is that is completely left alone by those 3 automorphisms? Can't be, alpha can't be in it. What seems to be left alone? Omega is what's alone. Everybody agree with that? So corresponding to this thing, this field,
The last 2 columns?
yes, the identity in the last 2 columns.
I thought you said 3. And I was like, okay.
Right.
I'm on board.
So these omegas are left alone. And so actually you can do the computation and show that the subfield of this thing that is fixed by these 3 automorphisms is exactly Q omega, which is a quadratic extension. You've taken Q and you stick on the cube root -3, if you like. Notice that this is 2, and this degree is 3, just like over here. And there's 3 other fields that correspond to. So for example, what about this one right here, E12? What does it look like the subfield is that is left alone by the identity and phi 1, 2? I probably shouldn't have started with that. Let's start with probably easier to see. How about phi 2, 3? Let's go all the way over this one. Can you all pick out the subfield that's left alone? What's left alone by phi 2, 3? The alpha. Everybody agree? This one's actually going to be Q alpha, which is the cube root 2. Notice this extension. This is index 2, and this extension is 3. How about 1, 3? If I pick out what's left alone by 1, 3, it might not be in the tape. Oh, it isn't. It isn't. Q omega alpha. How about the last? How about Q P1, 2? What's it now? Yes, you are correct. But I'm going to do it this way. The fields are actually the same, right? Because notice that this thing squares to what you're picking out here, right? And the reason I did this is because these 3 are the roots. But actually, if you take the field and join with your omega alpha squared, you will also get this element in there as well. That might be a nice thing to check. So basically, this right here, we're gonna go through it, and the devil's in the details, we've got to work some of the stuff out for sure. But this is basically fundamental theorem of Galois theory right here. You have your Galois group, and in the case that we're going to be concerned with, it's mostly going to be finite. And that makes this really great because finite groups have only finitely many subgroups. The subgroups correspond to intermediate fields. And if they're normal, you get a little bit of extra oomph to it, as a matter of fact. And you get a lattice just like this. So is everybody okay with that so far? Okay. All right. So I like that example because I think it illustrates a lot. We saw, I'm going to record this here. We saw earlier that this is the identity, and that's kind of the seeds of this. The Galois group of Q alpha omega over Q, using the notation of the previous example, is S3. Let me also point out, and I guess it's probably worth me recording, it's rather silly, that the Galois group of any field over itself, the automorphism of a field that fixes itself, the identity, kind of silly, I guess. You might want to guess at this one. This was kind of I'm not going to go through the details. I'll tell you what the answer is. You can see if you can figure it out. If I won't guess. So what I'm asking here is, what are the automorphisms of Q adjoined with the square root? So this is the smallest field that contains both the square root of 2 and the square root of 3. Anybody want to guess the automorphism structure here? If it were just Q radical 2 over Q, it would be Z2, right? Because that's that earlier example we did, Q adjoined with the square root of D. And if it was just radical 3, it would be Z2. So the automorphisms you have are basically swapping out 2 with its negative and radical 3 with its negative. Actually, this one is Z2. We'll take a look at that later. Okay. Any questions on that? Okay, so now we're going to climb the hill. Start climbing. Because I made some really kind of wild claims about subgroups corresponding to intermediate fields and so forth. So we start this off. Like I said, keep this table in that previous example in mind, and that's kind of the seeds of a lot of what goes on in Galois theory. Like K inside E inside F be fields. And H, a subgroup of the Galois group of F. So H is just a group of automorphisms. H prime when I do the prime, so this prime notation that I'm going to introduce here in this theorem, when I hit a group with a prime, it turns it into a field. When I hit a field with a prime, it turns it into a group. So this is a corresponding. So what do I mean? This is all the stuff in F such that sigma V equals V for all sigma in H. is a field intermediate to the extension K. So this is everything in F that is left alone by everything in H. So the H prime, that descriptor comes from the fact that my automorphisms come out of H. B, E prime, I hit a field with a prime, it becomes a group. This is all the sigma in the Galois group of F over K, such that sigma E equals E for all E E. This is a subgroup of the Galois group. I'll look this proof in the notes as an exercise, but let's at least outline it. So for the first statement, we'll see what we got to do. Certainly, let me make that observation. The fact it's in F is by definition, and the fact that it contains K comes from the fact that everything in H is a K automorphism. So in particular, everything in H fixes K. So if everything in H fixes K, then it's got to contain K, right? So step one, I put it where it belongs, right? Yes, it's intermediate to K and F. It's certainly a subset of F. Why do we have to show? So I'll just show that it's closed under addition and multiplication. So 1, B2, B, H prime. Then, so this means sigma B1 equals B1 and sigma B2 equals B2. Therefore, for all sigma in H, therefore sigma B1 B2 B1 B2 and sigma plus B2 also. So it's closed under addition, multiplication, the rest is pretty easy. B. Well, this is certainly E prime is a subset of the Galois group of F over K by the very definition. Now what we have to do is show it's a subgroup. Right. Let me also point out that the identity is in here. So I probably should have done this. The identity on F is in E prime. So I know that I've at least got the identity in there because the identity certainly fixes everything in E. I don't care what E is. What we have to do is we need to show sigma 1, sigma 2 inverse is in E prime, but if you look at sigma 1, sigma 2 inverse of E, well, let me structure this better. Since sigma 2 of E equals E for all E and E, then composing by the inverse, again, sigma 2 is an automorphism. E equals sigma 2 inverse for all E and E. So sigma 1, sigma 2 inverse of E is sigma 1 of E. And so that establishes that claim. Let me make a couple real quick remarks here. H prime in this notation is called the fixed field of H. Let me also point out that 1 prime is all of F. Like that, the thing F is certainly fixed by the identity, but care needs to be taken here because not necessarily. Not necessarily K. And you might think about why that's true. In fact, look at one of the examples we did earlier. Okay, any questions? Or any questions out there? All righty. Well, you all have a good one, and I will see you at least by Wednesday.